Refraction, thin lenses. Take a look. First, we need to understand what refraction is. Okay? We're going to have two types of lenses. Convergent lenses and divergent lenses. Now, what is a lens? It's a transparent object that refracts light rays such that they converge or diverge to create an image. Now, when it says refract, what does it really mean? The refraction of light is what you see here in the picture. Take a look to the light rays. The light rays are coming in this direction, okay? But once they pass through the lenses, the direction changes. Well, this one doesn't change the direction, as you can see, and the reason is because this ray, the second ray, the middle one, is coming at a 0 degrees angle, so it doesn't refract. But the other light rays that are getting in at a different angle, yes, they will. This process that you see right here is known as refraction. Now take a look to the first lens, this one, A. This is called a convergent lens. How do you recognize a convergent lens? Because it is thicker at the middle. Okay, so what happens here? In this point right here, I'm going to put it in a different color. As you can see, in that point over there is where all the light rays are coming in. So in the end, the light rays are going to be in the same position. Now, we're going to know later on what this point means. Now, in part B, we have a divergent lens. As you can see, in divergent lens is thicker in the edge, okay? Take a look. Just compare it to the size of what you have in the middle. Now, take a look what happened in convergent lens. The light rays, after they pass through a transparent object, which is the lens, okay, the light rays will also refract. But in this case, as the name says, the light rays diverge, okay? So they go outward in different directions. So, as you can see, this is very similar to what we have been learning in mirrors. But there is a big difference. In mirrors, let's say that this is a mirror. In mirrors, the difference that we have is that the light rays are coming, they touch the mirror, and they are reflected. In mirrors, we have reflection. In lenses, we have refraction. That is a big difference. The main difference between the two topics is that one. In mirrors, we don't see what is behind the mirror. That's why we call the image to be virtual. But here in lenses, we can see the objects through the lenses. That's why if you're blind, you use lenses. Lenses will help you to visualize better. Now, there's a big difference between the two of them. Remember, in mirrors, we have reflection of light. Light is being reflected. So the light rays touch the mirror and the light rays are reflected back. but in the lenses, the light rays pass through. Now, I know that this is kind of boring, so I'm gonna stop sharing because I need to show you something to make it more interesting. Now, I'm not going to ask you to do a project like this, it's just too much, but it's very interesting, okay? Okay. Okay, I'm gonna let you know what he's doing. Remember that we were working with mirrors. And I told you, okay, that's the focal length, that's the radius of curvature, that's this, that's that. But you don't know what that is. Now, I'm not going to show all the video because, no, I'm not going to. I'm just going to show you what he's doing, okay? So take a look. He's making there a circle, okay? You're not listening, right?
No.
Sorry. Yes. It's that these options are always disabled.
That's it for the forming plate. It's now time to take a look at the Mylar sheets. Like I said before, aluminized Mylar is sold as space blankets, and they come folded up into a tiny package. Before this material can be used to make a mirror, it first needs to have as many of the wrinkles taken out of it as possible. A simple wood frame in the shape of a square and just larger in diameter than my PVC plate should work.
Okay.
I worked on one side at a time.
The space blanket that he's using over there, as you can see, it was folded in well, many parts, and it doesn't look smooth, okay? And because he wants a mirror, he's gonna smooth it with this technique.
Attaching the Mylar to the top side of the frame, then flipping it over, I pulled it tight to take out the wrinkles running parallel with the ground. By repeating the process on the left and right side, I was able to also pull out the wrinkles that ran vertical. I could get this tighter, but this result should be adequate. The baseboard is prepared, and now so is the Mylar, so it's time to see if my method will work. From some tests I did earlier, I found that epoxy is the best adhesive for adhering Mylar to PVC, so I'll carefully spread a layer around the outline of the circle. The Mylar is then lowered on top and pressed into the adhesive to get a good seal. To provide air pressure, all it takes is a bicycle pump. Though I tried this small one first,
In that moment, you see that it's not a convex mirror or a concave mirror because it's totally plain, okay? But then, well, he continued working on it, and there in this part, he began
here I can begin
using
inflating the mirror. I'm not sure how far I can push this Mylar before it
forgot the name.
pops, but fortunately
And I just bought a bottle of this foam. It's foam.
it forms a parabolic shape almost immediately. What I haven't talked about yet is how I plan to hold the mirror in this shape after it's been removed from the base plate. My first test was to cover the Mylar in spray foam. When it hardened, I was hoping it would have stuck to the Mylar, holding the curve in place. This resulted in about the saddest excuse for a parabolic mirror that has ever existed.
Disaster.
Fortunately, it only takes a few minutes to scrape off the base plate and try again. After inflating this second sheet of Mylar for another attempt, I decided to try molding the mirror with fiberglass. Watching the resin flow over such a smooth curve was pretty cool to see. Once it was spread evenly, I lowered the first sheet of fiberglass on top. I noticed at this point I had a...
You know what fiberglass is?
What,
Guys?
miss?
Fiberglass, the material he's using right now. Do you know what that is?
No.
Okay, that is a material that people use to make different shapes. For example, my neighbor across the street, he has a workshop from this thing. And many people go there because they want to tune the cars, el tuneo de carros, you know. So in the end, what they do is they create like they're very artistic, okay? Because the fiberglass it has that ability that you can work with it and create different forms. So he can make many things from it. Maniquíes, toboganes, things like that, but also things for your car. If you want to modify a part of your car for the car to look awesome or more sporty, I don't know, people like it. Sobre todo taxistas, they like it a lot more. And they like to modify their car by using this kind of material. So what I want to say is that the fiberglass is a very cheap material, but when you finish to work with it, it's very solid. Okay, so his choice here is a lot better than the foam that he used initially. That was a failure, but here he basically does that correction. But I want you to see the final result.
Small leak, so until the fiberglass cures, I'll have to occasionally add more air. In the meantime...
Do you know what cure is in this kind of explanations? When it says the fiberglass cures, do you know what that is? Okay, the curing methods are just waiting for the materials to be ready. In this case, for the fiberglass to be completely solid. And that requires a time that is provided by the manufacturer from the fiberglass. It says, cure time 24 hours, cure time 12 hours, 1 hour, 30 minutes, okay? So he said, after the fiberglass cures, so when it gets, when it hardens, in other words.
I added 2 more layers, and to accelerate the cure time, I heated the mirror with a hairdryer. The mirror I made for my first attempt using the spray foam was damaged when I simply tore it off the plate, so for this one, I'll cut the mirror off using an angle grinder. Finally, I get to see the result. Once cleaned up, the reflectiveness is actually very good. The fiberglass is just a little too flexible and wants to curl up like a taco shell. If it's pressed against a flat surface, it still holds the parabolic shape. I just need something to keep it there. I found this plastic landscaping trim that seems...
So yes, it doesn't keep the shape nicely like he was expecting. So he's going to reinforce all the mirror, okay, the edge of the mirror for it to be completely still. But I want you to see how it works.
Made from a $1 space blanket. I think an even smoother surface should be attainable if I inflated the mirror a little more before laying on fiberglass. My sponsor for this video is Rayton Solar, a solar panel manufacturing and development company working to create higher efficiency panels. Use of a particle accelerator eliminates waste, which means the best quality of silicon can be used without increasing the cost over lower quality panels. Better silicon translates into better power conversion and a more efficient solar panel as a whole. If you'd like to learn more about Rayton Solar, they're currently running a crowdfunding campaign that you can check out through a link in the video description.
So what he's doing right here in this moment, take a look. I don't know if you get to see, but in the end, what happens is that the light is being reflected, okay, at a certain point. The point in which all the light rays join, that point is what I told you is the focal point of, in this case, of a concave mirror. In this focal point of a concave mirror, all the rays concentrate, and the energy here is so high, for that saying, that is able to burn whatever you put in front of it. So yes, it could be considered to be a dangerous weapon, or people use it as a solar stove. Okay, so it's quite interesting. I mean, I know you don't like the physics class because it's so boring. She's always talking. We never talk. But in real life, in the end, the applications are what really matter, you know. And honestly, I would like to ask you to work in projects like this, but I know that once COVID, two, it's dangerous somehow for you to work with something it's not too complex, but it could be dangerous. You could get burnt, okay? So, but it's a nice way to learn. And that's why during the week 9, this is what the project is going to be about. It's going to be about you learning physics by doing physics. Now, it's not going to be something too complex like this, but yes, you will be able to apply the concepts that you learned in class in your final project for that week 9. Marianne, your camera must be turned on. So I'm going to be sharing with you in Google Classroom a video. There's another video, but I don't know. I thought it was this one because it's the one that seems like I watched. And yes, I watched it, but I also watched another video that you can actually see the light rays. And it's very interesting. Now, here is what I was telling you. This is a video. Wait. No, qué raro. Okay. No, it wasn't a video. I thought it was the video. I know that it had a video over there, but I cannot see it. I don't know why. Okay. So maybe we don't see the lenses like this. Aria! Wait a second, my cat is... Okay, so notice this. Now the difference, okay? Now take a look. Here are the light rays, okay? And they will pass through, when they pass through this thin lens, in the end, you can see the refraction of the light rays, okay? The one that is coming completely straight, I mean all of them are coming completely straight, but this one that is coming precisely in the center of the lens, okay? This one does not refract, but the other two light rays, you can see they do. They refract. And this point right here, the one that you can see right here, is what we know as the focal point of a thin lens. Okay, it works very similar to mirrors. Very similar. Not the same though. Okay. Now, as I told you, like mirrors, lenses form images, but lenses do so by refraction instead of reflection. That is the main sentence or the main idea to understand. Mirrors make images by reflection of light, and lenses form images by refraction of light. The images formed can be real or virtual depending on the type of lens and where you place the object. Virtual images form at a point from which light rays appear to come but do not actually come. Real images can be projected onto screen. Virtual images cannot be projected. Virtual images are those that we cannot see. Okay, application of thin lenses. They are commonly used to form images in optical instruments, such as cameras, telescopes, and microscopes. I think you're familiar with the three, okay, with the three instruments that I mentioned. Cameras, most amazing thing. I mean, internally, how a camera works. Take a look. All you can see right here are a big set of thin lenses, okay? Now, do you see my screen?
Yes.
Okay, okay. So, the light rays come inside the camera for that saying, and they pass through all these lenses that you see here. And then, take a look. It has a mirror internally. This mirror is a reflex mirror, so it's going to reflect the light, okay? And then this is a prism, okay? A pentaprism, it means it has 5 sides, so the light rays are gonna be reflecting, and in the end, this is the side where you put the eye on. You're gonna be able to see what is in front of the camera. So everything, or almost everything that we, not almost everything, we could say everything that we are, every technique, every material, every object, every technology that we use uses physics in the end. But the lenses are very interesting. Now, our human eye also works or acts like a lens, converging light toward the light-sensitive retina at the back of the eye. Take a look. We have the anatomy of the eye, okay? We have the one part of the eye that is called the lens. What's the purpose of the lens? The same purpose that we know that lenses have, okay? Allow us to see. So this kind of lens, in the end, it's going to be, remember, the light rays are going to come in different directions. And in the end, they're going to refract, okay? At a certain point here, behind. And how well your lens is going to allow that you see better or not. And that's why when you start to have sight issues, like me, for example, this year, you're gonna have the need to use lenses, glasses, okay, to fix the what is wrong with your eye. So even our body uses physics. And also a telescope. A telescope works similarly to the camera system that we have here. As I told you, two types of lenses, convergent and divergent lenses. Okay, a typical lens consists of a piece of glass or plastic, so that each of its surfaces is a segment of either a sphere or a plane. Okay, so remember, the curved mirrors, are portion of spheres, and lenses too, but also of a plane. Notice that the lenses are shaped differently. Okay, converging lens are those that look like an almond. Okay, and the divergent lens, I don't know, it looks like, well, nothing comes to my mind in this moment. But the converging lens look like an almond to me, so it's easy for me to identify. So, characteristic of a converged lens is that the lines tend to meet at a point. In the diverged lens, lines separate from their root and go in a different direction. That is the main difference between them. So the lens that is thicker in the middle, the one that looks like an almond that I said to you, is a convergent lens, and the one that is thinner in the middle and the edges are thicker are called divergent lens. And the light rays show why the names convergent and divergent are applied to this kind of lenses. The focal length, we're going to have focal length here, is the image distance for an infinite object distance. As with mirrors, it is convenient to define a point called the focal point for a lens. Unlike mirror, lenses have two focal points, one on each side. Okay, because as you can see, it has the surface where the lights are coming in and the surface where the lights are coming out. So it's going to have a focal point here, but also a focal point right there. So the sketch of this is going to be a little bit more interesting. Okay, in the distance from the focal point to the center of the lens is called focal length. The focal length is the image distance that corresponds to an infinite object distance. Ray diagrams of thin lens systems help to identify the image height and location. For a convergent lens, this means that light will come together at a focal point in the back of the lens. The front of the lens is defined as the side of the lens that the light rays first encounter. So, lights come from the front of the lens and they pass to the other side, to the back of the lens. In the back of the lens is the exact position where the image is going to be formed. The back of the lens refers to the side of the lens opposite where the light rays first encounter the lens. I know that it looks and is read as pretty obvious stuff, but in the end, it matters. Now, characteristics of lenses. Convergent lenses can produce real or virtual images, just like the mirrors. As a distant object approaches to the focal point, the image becomes larger. When the object at a focal point, I'm going to show you the diagrams later, the light rays from the object are refracted so that they exit the lens parallel to each other. When the object is between a converging lens and its focal point, the light rays from the object diverge when they pass through the lens. Okay? Take a look here. Take a look at that ray diagram, similar to the ones that we have been using. So, divergent lenses can produce virtual images from real objects. take a look here. Here are all the rays, okay, that are coming from the object. And of course, they're going to be projected in the back of the lens too. Notice that I have two focal points, in front and in the back